Swayam Prabha. Digital India. Educated India.
Now, these are the molecules, right? Now, column podala. Okay, I am just drawing some number of. Now, let's say this is a structure of whatever I am trying to cut, right? I am trying to understand what kind of force shall I apply in order to cut. That is the question, correct? Supposing I apply a blade, I will separate it, correct? Yeah. If I apply a pair of scissors, what I would do is apply like this and apply like this, correct? There is a clue. Coming in? Yeah, no, this is a long, I am just taking the thickness which has, let's say, 4 layers. I am just drawing that way. Yeah. Simultaneously? Okay. Okay, so let me give another clue to you. You have heard of graphite? What do you know of graphite? Huh? Conduction. It can? Conduct, okay. Graphite. What do you know about graphite? So what if it is layered? Everything is, this is also layered. See, layered. The layers? Why?
So they are held by weak forces, so weak van der Waals forces. So
everything is held by weak van der Waals forces. Why not? The question I have is why not? It can also bond the other way, correct? Oh, sp2 is only planar? If I have charcoal, if I have some other form of carbon, it's possible, no? What is it that helps graphite to be layered? The answer lies in one single fact. Supposing I look at it this way, I look at it this way, I look at it this way, and count the number of atoms per length, right? Do I get any information? Yeah. Now I can do the same thing for surfaces also, right? So if I have 2 surfaces and I want to find out the density of the atoms, if I take this surface and this surface, will they be different? They'll be different. First thing, right? It will be different, correct? Which also means that I can figure out dense layers and not so dense layers. Yes or no? Why am I thinking about it that way? Not so dense layers? It's easy to separate, correct? Now let's answer the question. If I talk about, let us say, a metal, aluminum, what crystal is that? Aluminum, titanium, steel, crystal structure. You have not studied. Yes or no? You have not studied. Oh, you have not studied. Okay, sorry about that. Okay, each one has a particular crystal structure. It's called face-centered cubic or body-centered cubic. Suddenly there is a nod. Have you read or not? Okay, you read by yourself, not in your subjects, right? So the arrangement can tell you there are certain planes where it is dense, which means that an atom is closer to the other atom along that surface compared to another surface that I am looking at. And if you look at metals, the way the metallic atoms are arranged is such that I can discover so many planes along which the atoms will be arranged in a dense way. So if I have one set of atoms in a dense way, and then since it is a periodic arrangement, there is one more set of atoms which form a plane. Between these two dense planes, can it not slide just like graphite? Correct? We call that as slip, S-L-I-P, slip. Metals have lots of such slip planes through which they can just slip. Okay? Slipping is different from separation. Correct? What's the difference? If I have two objects, right? Separation is like this, correct? Slipping is like this. They're still intact. Correct? But deforming. This is deformation, right? Deforming, correct? Now, if I keep on slipping it at a particular extent, it will just come out. But it is easy to slip this compared to separating it. Correct? And therefore, when I use a pair of scissors, I am basically moving one layer over the other. In order to move that layer, how am I applying? Along the plane. And we call that force or stress as, now you can tell me, shear stress. Does it mean that there is some other stress? The answer is yes, which is normal stress. Okay. So now I distinguish between normal stress and shear stress, right? If the material is dominated by slipping, it holds on to itself. But if it is dominated by separation, it cannot hold on to itself. How does that translate to in terms of the property of the material? Anybody? Oh God, I am only in the second slide here. Yeah.
Let's say if something's stronger in terms of slipping.
I agree.
No.
I definitely agree based on how its arrangement are. Now, if the arrangement is such that sliding is easier, it will give me some property. If it is such that sliding is not easy, it will give me some other property. I am now asking you, what could that property be? Huh? No, elasticity is reversible deformation. Correct? Nothing to do with, see, separation again is a failure, or the other one is also failure because it is just slipping. It's not going to go back. Once these two sheets, Where are they? Where are the sheets? Yeah. Once these sheets are moved, they will not be going back. Correct. Which means deformation is not elastic. Correct. Similarly, if it opens up, it will not go back. Reversed. Correct.
Then you need less amount of force in order to initially
We
deform
don't
it.
know less amount or not, but you need less amount of stress to slide
Yeah.
compared to this. Wonderful. So, there are materials where it is easier to slide and there are materials where it is easier to separate. Correct? But there is a name to such materials at a macro behavior. And you all know about that behavior. That property. Chocolate question. Chocolate attracts your mind to answer. Yeah. One is slipping, which means it is intact, but still it has deformed. The other one is separated, which means it has become two. What property is that? What property is that? Yeah, you know it here. Huh? Wow, here, Ashika. One that separates is brittle. How do I know? It has to reach my ear, no? No, I don't remember. Anyway, I'll give you chocolate also. What about this, the one that is slipping? Huh? Ductile, correct? So I can now separate the properties of the materials to be ductile materials and brittle materials. Give me an example of ductile material. Sheet of paper, plastic, metal, plastic is not ductile. Come on, yeah. You have your chocolate wrapper, no? I'll give you a chocolate later, but you pull it, you will be able to stretch, no? Ductile. Correct? Yeah. Examples of brittle. Glass, very good. Oh my God. Is it brittle? Yeah, it's brittle, no? Okay. Charcoal. Chalk, correct. Chalk. Ceramics. Huh? Bricks. Concrete. Right? All these are brittle. And ductile materials, metals, and so on. Now let's ask this question. When will you use a pair of scissors and when will you use a knife?
Knife is for
Good, no? Now we are able to understand. Where I'm aiding sliding, I will use why scissors? I'm applying shear stress. Wonderful. So where it can easily, I'm going to use this word, fail by sliding, I'll apply shear stress. The other one is when I bend, actually what I'm doing is I'm applying normal stress.
sir. So it will, if the paper is like this, when I cut like this, the paper will go like this, or
So paper will actually go this way.
the thinner
Yeah. So
along the thickness.
if you look at the paper, I'm going to use this so that it's easy. When I do this cut, this is trying to push it on the same plane as this, almost the same plane. So it is trying to push this and push it the other side, and therefore it is affecting sliding easily. Yes, correct. It is along this thickness that it is sliding, and if it is easy to slide, I use this. Correct? Yeah, and therefore can I use a pair of scissors for this? Because I am applying what? So from today, we will not use this name a pair of scissors. What shall we call this as? Shearing instrument. Wonderful. What is this? Shearing instrument. So this is a shearing instrument. Use a shearing instrument. Can I use? No? What will happen if I use? Huh? Hard is fine. What will happen? It won't cut properly, correct? Yeah, it won't cut properly. You can see it, right? Though it cuts, it's not uniformly cut. Just like what we did for a plastic like this, correct? Both are plastic, by the way. I'll tell you what the difference is. But here it's very smooth and nice, correct? The reason is I'm able to locate slip planes along which it can happen. Usually, glasses are what kind of materials? One more understanding. What is that material? What line material? Crystalline material. Metals are crystalline materials. This is amorphous material. Amorphous material, it's very difficult for you to find out some plane along which you can move it, because it's very zigzag. So like a rough plane, correct? And therefore it's very difficult. It's just a visual understanding. Is this clear? Yeah? Okay. I'm going to move on, but I may stop somewhere, okay? Metal, sheet, plastic, we have understood this now. A piece of chalk, and therefore how will I break it? How did I break this? How did I break this? What did I do? Bend it. When I bend, I am applying what? Normal stress along the thickness. Right? Understand that? We'll come back, revisit it in order to use it for something else. Okay? Now, this is for glass. Yeah? Chalk. Where is the chalk? Yeah. So, shall I cut it? No? How shall I break it? Yeah. There are two ways of doing it. One is pulling it. Shall I? Huh? Yeah, I can break it. Right? The other is easier one, which is bending it. I don't know, this is the right time for you to understand why bending is so easy compared to that, but we'll come to that later. Okay? So, this is a brittle material. What do? I apply normal stress. The other one is shear stress. Wonderful. Okay.
Is both bending and pulling both are normal stress?
Bending.
Bending and pulling, both of them are normal stress?
Actually, yes. I'll just explain for a layman. Okay, is that okay? Supposing I pull it, let's say this is a piece of chalk that I'm pulling. It will be like this, and if I look at this cross section, the cross section you will see stress like this, correct? Normal to that plane. If I take the piece of chalk and I bend it like this, it will stretch this part and compress this part. Again, if you look at it, it is along the axis, correct? And this, it cannot hold. And the amount of moment that you need to apply is very small compared to the force that you have to apply over here. Okay? Questions? Is this clear? Yes. Wonderful. Now, I'm going to move on to many other things, but Is this ductile or brittle? Huh? Neither. Hey, come on here. Okay, supposing I make it flat. I make it flat, okay? Can I use a pair of scissors to cut it? Why? Why? Because it is a ductile material. Very simple, yeah. See, I can cut so easily. Haven't you used clay? Cut a pair of scissors to cut clay? You have not done that, no? You have not done that? Okay, you can easily cut. Right? It's a ductile material, and therefore, the reason why it is ductile material is because sliding is happening, but it is intact. So even if I pull it, it is still a single material. Yes or no? Yeah. Only thing is, it is quite ductile. Yeah. Is it ductile? How fast I apply? Correct? It seems to depend on the speed at which I apply, correct? And it is perfectly like how a chalk piece breaks. It breaks. Clay breaking. Clay breaking. Yeah? Okay. Why is it happening? Because, from a layman understanding, because
Impulse.
the speed at which I apply. Okay. If it is getting strained, how do I explain fast straining, slow straining?
Sir, impulse.
How do I, what parameter do I use?
The time
Fast
is very.
straining, yeah, time
The
is
time
less.
is very less.
Yeah, so what shall I use?
High force, less time.
Straining it and
Not allowing it to recover.
correct. How do I insert time to that parameter called strain? Strain rate. Correct? By the way, you can even break water. You can break water. Yeah, I understood what he's saying, but I wanted a parameter, which is strain rate parameter. Water is also breakable, right? Okay. Now, I'm going to ask you this question. Where is that here? The same glass sheet. Yeah, you have a question.
Sir, most of the ductile materials also, if they are thin, they become brittle, right? If they're very thin, I'm saying.
No, see.